Today I'm going to look at using the Kinematics Ramp that we have for use with the collision trolleys and the ticket timer. It's an incredible piece of construction because it saves you a lot of work, but one of the things I learned today is something I had learned many years ago and totally forgotten, is that when you order some equipment you must make sure that all of the equipment comes with it. This is the stand for the Dynamics Ramp. You open the bottom up, you set the legs like that, and you'll notice that there's a fixed rung at the bottom which actually helps with stability. Then you have all these holes up the side, and lo and behold, I did not check to see that the doweling that went through there was actually present in the kit. Somehow or other it just didn't get collected. To that end, I grabbed hold of some conduit, and by using that conduit I cut a piece off, bent it over just from the end piece, cut it over, bent it over, and this fits through this rather difficultly, but it does, and that's what I'm going to use. Lesson well learnt. Following this, it's pretty straightforward to set up the ramp. There is a piece of timber underneath which allows you to stand over the little rail here so that it hooks onto it and won't move after that. That gives us stability. It's very stable. And then down here we have the little foot which we put in, which stops the thing from going all over the place when it comes off. This setup now is ready as the ramp. The holes on the stand, if you measure them, are exactly 4 centimetres apart. That's 24, that one's 28, that one's 32, that's one 36, etc. The ramp part, that is the base of the ramp that the trolley rolls on, is that line that runs down there, and that's exactly 21 centimetres high from the ground. That's this part here in that corner, 21 centimetres. At the other end, the bottom of the bottom of the ramp, the surface part here, is exactly 3 centimetres from the ground. The length of this ramp, from where I have my finger at the base of where we took the height from, up to where the ramp here meets this upright, is 110 centimetres exactly. This is a right angle triangle. Right angle here. This is the vertical height of the right angle triangle. This is the hypotenuse of the right angle triangle. This length, as we measured before, is 110 centimetres or 1,100 millimetres. The height of this to the bottom there, that mark there, which is the surface of that ramp, is exactly 21 centimetres. Now that makes the difference in height from the bottom to the top. 21 centimetres minus 3 centimetres is equal to 18 centimetres. The 18 centimetres, which is 180 millimetres, is the vertical height. You divide that by the length of the hypotenuse, 1100 millimetres, and you get 163,636, so divided by 11, so it's repetitive. So 0.1636 is the sine of that angle, because the sine is opposite over hypotenuse. We only need the sine of the angle as far as any of the work goes here, because g sine theta is always in the calculations when you're working with the acceleration due to gravity, little g. The value of the angle is not even a problem, but you could easily work it out. If the sine, it's a small angle, so if the sine is 0.1636, the angle is about 0.1636 radians, and if you multiply the 57 degrees roughly in a radian, divide that by 5 on 3, which is pretty close, 0.6, That's about 9.4 degrees if you wish to do it that way. Of course, we don't need to calculate what the actual angle is at all. That's the advantage of this particular device that we have here. We don't need to calculate what the angle is because it's the sine that we need. And in all cases, the sine is just purely the ratio, the height divided by the length. The length is constant, the height is very obvious what it is, and that's all we need for the calculations that are involved using the dynamics or kinematics ramp.